building these really powerful quantum computers, it's running into some walls, right? Like qubit counts and keeping them stable, uh, coherence.
Yeah, coherence is a big one. Keeping those quantum states just right for long enough.
Exactly. So this idea is popping up more distributed quantum computing, basically linking multiple quantum processors together.
Mm-hmm. It's kind of the next logical step, thinking about how classical computing scaled up with networks like the internet.
Right. Connect smaller systems for way more power. And for you listening, we're diving into this really neat simulation today. It gives us a peek at how this interconnected quantum future might actually take shape.
Yeah, the sources you share lay out this model. It's got these simulated agents in different quantum environments trying to find each other.
And they're managing their qubits, those super sensitive quantum bits, trying to get them entangled across these simulated spaces, and even attempting some basic communication.
It's definitely simplified. I mean, it doesn't capture all the weirdness and complexity of real quantum mechanics.
For sure. But it still gives surprisingly good insights, doesn't it, into how these distributed systems and quantum principles might, mesh together.
Absolutely. It provides a framework, a starting point for thinking about the huge challenges involved.
So that's our mission for this deep dive, unpacking this simulation. We'll look at how agents find each other, how the qubits and entanglement work in this model, and how they try to communicate or confirm their connections.
Okay, so first up, finding each other. In any distributed system, you need some way for the pieces to, well, discover the other pieces.
Right. And the simulation uses something pretty straightforward. A central global discovery service. Think of it like a shared address book, basically.
Yeah, dictionary in the code.
Yeah.
The AI agent instances, they register themselves using announced presence. They say, here's my simulation ID, my agent ID, and my qubit index.
Then, if an agent wants to find someone else, maybe in a different simulation, it uses Discovergence to query that central book. It gets back the details it needs.
It works for the simulation, but, that centralized approach.
Hmm.
It immediately brings up real-world issues, bottlenecks, single points of failure.
Like DNS in the real internet or tools like Console, they're much more spread out, more robust.
Exactly. And the simulation kind of hints that maybe future agents could be smarter, perhaps looking for partners based on specific quantum capabilities, not just an address.
Okay, let's switch gears to qubits. The simulation has this qubit class. Now, real qubits have superposition existing in multiple states at once. Super weird.
Uh-huh. The simulation simplifies that a lot. Here, the qubit state is just a random classical 0 or 1.
But crucially, it has this entangled with property, right, to show it's linked to another qubit.
Yes, and the entangle method connects two qubits, but only if they're in different simulations and not already entangled. Then it assigns them the same random classical state.
So they're correlated in the simulation.
Right, and the measure method just returns that state. If they're entangled, measuring one effectively tells you the state of the other one instantly in this model.
Which is, again, a simplification. Real quantum measurement on entangled pairs gives you correlations, strong ones, but it's probabilistic, governed by things like Bell states, not this deterministic link.
Precisely. It captures the idea of non-local connection, but not the intricate physics.
So how does this entanglement actually get set up between simulations?
Well, each simulation environment has a quantum interface. Think of it as the qubit manager for that simulation.
Okay. And agents use qubit via this interface.
Yep, it makes a qubit associated with that agent and keeps track of it. Then there's attempt entanglement.
Ah, this sounds key.
It is. An agent gives its local qubit, tells it which other simulation and agent ID to target. The interface tries to find the target qubit in the other simulation's interface.
And if they're in different simulations, not already linked.
It calls the local qubits entangle method. And it checks afterwards if the entangled with property confirms the link was made.
Got it. So this whole simulated interaction mirrors the massive real-world challenge of actually creating and maintaining quantum correlations across a physical network.
Exactly that. It's the quantum internet problem in miniature.
And the agents themselves, the AI agent instances, they're actively doing stuff.
Oh, yeah. They use Discovergence, like we said. Then they run solve entanglement partner problem to actually pick a target and try that attempt entanglement.
And they try to communicate, too.
In a very, very basic way. Send message essentially flips the agent's qubit state based on message bits. Receive potential message involves measuring the partner's entangled qubit.
Ah, the one in the other simulation.
Right. And comparing its state to the partner's last known measurement, looking for anti-correlation in this simplified setup. It's rudimentary.
Plus, they share information, right? Using share information and
So,
receive information.
yeah, things like entanglement tips, untangling protocols, channel status labels for data they swap. They also synchronize histories to compare their measurement records with their partner.
So they're trying to sort of cross-reference and see if their measurements match up in the way they expect if they really are entangled.
That's the idea. It's their way of trying to verify the quantum link using the limited tools they have in the simulation.
Okay, it's crucial we underscore the limitations here. We've mentioned them, but just to recap. Classical states. Entanglement is deterministic. Communication is super basic. Discovery is centralized.
And perhaps the biggest one, absolutely no noise or errors are modeled. Real quantum systems are incredibly noisy and fragile. That's a monumental difference.
But these simplifications aren't failures of the model, are they? They're necessary to even begin studying these concepts.
Absolutely. You start simple to understand the core logic, the discovery, the linking, the attempted communication, before layering on the immense complexity of real-world quantum physics and engineering.
So, the big takeaway for everyone listening, even with these simplifications, this simulation gives us a really valuable handle on the fundamental concepts. How separate quantum systems might find each other, connect, interact. It's like seeing the first basic blueprint for a quantum internet.
And connecting that to the future, you can see the potential. Distributed quantum sensors working together, truly secure communication networks, running simulations on a scale we can't even imagine now.
It really opens things up, which leads to, I guess, a final thought to leave folks with.
Yeah.
If even these, pretty basic simulated agents can figure out ways to try and link up and share information across their simulated quantum spaces, what happens when we build more complex, real-world distributed quantum systems? What kind of totally unexpected behaviors or new problem-solving capabilities might just emerge from that interconnectedness?
That's the really exciting question, isn't it? What new things become possible when quantum computers can actually talk to each other properly? Really something to ponder.